In my Structural Engineering Made Simple series, today I talk about reinforced concrete beams with T-sections. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Reinforced concrete beams with T-sections, or as sometimes we call them flanged sections, are of two types. Those that are formed when a series of rectangular sections and slabs are cast monolithically, and those that are built or precast as T-sections. We call these as isolated T-sections. This figure shows a monolithic slab beam system. Therefore, T-sections and L-sections are formed. As you can see in this figure, a portion of the slab is contributing to the formation of the T-section. The overall depth of the T-section is h, which is measured all the way to the top of the slab. And the width of the web is bw. The clear spacing between the adjacent beams is sw. Towards the end, we have an L-section formed, again with a portion of the slab contributing to the flange. The width of the web is still bw. Also notice that the span of the beam is in the direction shown. Therefore, the length of the span L is measured in the third direction. If the slab and beams are non-monolithic, in other words, the slab simply sits on beams without rigid connections, no T-sections are formed. In this figure, the slab is not monolithically cast with the beams, therefore no T-sections are formed and the beams are treated as rectangular sections. Please notice that the overall depth of the beam is h, which is only the depth of the rectangular sections. It does not include the thickness of the slab. The width of the beam is bw, and there is no contribution from the slab to the formation of any T-beams or anything like that. It's just rectangular sections that are used here. Isolated T-sections. These are sections that are built with flanges, either cast in place or as precast beams. Applications are as pre-stressed beams in bridges and prefabricated joists for floor beams. The examples are shown in here. In this figure to the left, you see a pre-stressed T-beam which is used in bridges, and the figure to the right shows a series of prefabricated T-beams forming a floor system or a roof. The design procedures explained in this video are also applicable to other types of flange sections. Therefore, the following types of sections are treated just like T-sections in their analysis and design: a box section, a prefabricated floor joist, more like an upside-down U section, and an inverted T-section as shown in here. Inverted T-sections don't have any flange. However, the compression is in the area when the width is different from the rest of the beam, so more like a negative kind of flange. The recess that you see to the right and left provides support for floor joists to sit on. In continuous beams, the bending moment is positive, in other words, tension is at the bottom around the midspan, and negative, in other words, tension is at the top closer to the support. In such a beam, the cross section is considered the flange section designed for positive bending moment, since the flange is in compression. However, close to the support, the flange is in tension. And as such, for bending designed for the negative moment, the section is not considered as a flange section. Let's examine this in two figures. In this figure, the tension is still, as you can see, is at the bottom. Therefore, the flange is under compression. This is like a legitimate T-section or a flange section. However, the figure to the right, the tension still is at the top. The compression is at the bottom, therefore the flange is located in the tension area and has no contribution to the cross section. So even though it looks like a T-section, when we do analysis and design, it will not be treated as a T-section. These are the pertinent references used in the preparation of this video. I would also recommend that you watch lessons 7 and 8 of my YouTube series on structural engineering made simple. Lesson 7 discusses design of a rectangular section for bending, and Lesson 8 discusses shear design, which is also applicable to T-sections as well. Let's find out how we can determine the width BF. For T-sections, in other words, the ones with flange extended on both sides, as you can see in this figure again, BF is a minimum of the three values shown in here. BW plus 16 times the thickness of the slab, BW plus SW, BW plus ln over 4, where SW, as we said before, is a clear spacing between the adjacent webs, and ln is a clear span length of the beam. Remember that the span is in the third direction. ln is a clear span. In other words, is a distance from the face of one support to the face of the other support. When we have an L section, such as the one shown in this figure, BF is a minimum of the three values listed here. BW plus 6 times the thickness of the slab, BW plus SW divided by 2, and BW plus the ln divided by 12. Requirements on dimensions of isolated T-beams, and this is applicable to non-pre-stressed beams. For isolated T-sections, the following requirements on dimensions are specified by the ACI. Flange thickness T is at least equal to 0.5 BW, and the width of flange BF cannot exceed 4 times BW. So that means the effective flange width is limited to 4 times the width of the web. Bending resistance of a T-section. In our formulation of the bending resistance, from this point forward, we focus on cases where the flange is in compression. The bending resistance of a T-section depends on whether the compression area of the cross-section is extended into the web or is confined within the compression flange. These two cases are shown in here. As you can see in this figure, the compression area, which is represented by the dimension A, has extended all the way to the web. Please notice that the effective depth of the section is D. The overall depth of the section is H. Notice BF, which is width of the flange, versus BW, which is width of the web. As opposed to this case, the figure to the right shows a different case, where A is simply smaller than the thickness of the slab, and therefore the compression area is confined within the flange. However, all the other dimensions are the same. Now, the computation of the resistance Mn is different from this beam versus this beam. The question is, how do we know the compression area is extended into the web? To answer these questions, let's look at the following situations. Situation 1, a section geometry and the area of a steel are known. In this case, we first examine what we call a transitional case, where the depth of the compression area is exactly equal to the flange thickness. In other words, A is equal to T. For this special transitional case, the area of the steel will need to be equal to a specific value such as AST. Let's find out what this AST is. Let's find first the compression force, which is 0.85 F prime sub c Bf times T, and the tension force, which is AST Fy. And as you recall, F prime sub c is the compression strength of concrete, and Fy is the yield strength of steel. By setting T equal to C, we find out the amount of steel for this transitional case. However, in reality, our steel area is AS, is not AST. AST is just a transitional value. Now, if AS is smaller than AST, it means the compression area is limited to the top flange and A is smaller than T. Why? Because when AS is smaller than AST, that means the tension force is smaller. Tension force is smaller means compression force is smaller. The smaller compression force requires a smaller area than the entire area of the flange. As a result, A would be smaller than T. And if A is larger than AST, therefore A would be larger than T. Situation 2. We know the geometry of the section, however, we don't know the amount of steel. It yet to be designed. So how do we know whether A is smaller than T or larger than T? In this case, we know M sub U, which is the applied bending moment, which is obtained based on a structural analysis with load factors included. Therefore, the required strength for this beam is Mu divided by phi, where phi is the resistance reduction factor, and at this point we can assume it is equal to 0.9, which is usually the case. Furthermore, because we don't know the area of steel, we can assume D is equal to H minus 2.5 inches. At times you may want to go a little bit higher. If you suspect that you may have 2 layers of steel, you may want to go with H minus 3.5, but usually H minus 2.5 would work. Using again the transitional case, the depth of the compression area is taken exactly equal to the thickness of the flange. So you have the compression force and the bending resistance taking moment with respect to the center of the compression force. Usually we take moment with respect to center of tension force, but in this case, let's take the moment with respect to the center of the compression force. The moment would be C times D minus D over 2. And if I substitute for C, I get the transitional moment equal to 0.85 prime sub C BFT times D minus T over 2. This equation is independent of the area of steel, so we can always use it based on the geometry. However, notice that this is what we call a transitional nominal strength. In reality, what we need as a strength is Mu divided by phi. So if Mn, in other words, this required strength, is less than Mnt, it means the compression force is smaller than what we computed above, and therefore the compression area is within the flange, and A is smaller than T. If Mn is larger than Mnt, then A would be larger than T. When the compression is within the flange, in other words, A is smaller than T, as you can see in this figure again, compression is confined within the flange. We can write the internal forces as you can see in this longitudinal detail. The compression stress is 0.85 F prime sub C applied over the depth A, and therefore the total compression force is 0.85 prime sub C BF multiplied by A. The tension force is Fy multiplied by area of steel, and the lever arm is D minus A over 2. So please keep these equations in mind. And also remember that in this case, the width is equal to BF. Now, if you look at this figure, you notice that below this dashed line, practically the section would be under tension. So even if I had a rectangular section of this big, It would have been the same if A were exactly equal to this A. That is why this problem is very similar to a rectangular section. And the compression force is 0.85 F prime sub C BF times A. In other words, the shaded area here multiplied by 0.85 F prime sub C. And the tension force is Fi multiplied by As. Therefore, we can write the resistance in this case as As Fy d minus A over 2, where by equilibrium of the tension and compression forces, we can determine that dimension A. Please pay attention to this equation that Bf is used in this equation. There would be another equation for A that is coming up later, and in that one we have to use Bw. But for this case, when A is smaller than T, A is found from this equation. Also, we have to make sure that area of steel is larger than AS minimum. The AS minimum in this case is very similar to that of a rectangular section, except that we need to use BW in our equations. And as it is customary in rectangular section design, which is also applicable to T-section design, instead of these two minimum values, we can always use 4/3 of whatever AS is done by computations. So if we find out that our AS, area of steel, is smaller than these two, we can always use 4/3 of that AS as our minimum steel. And as indicated in lesson 7, we must compute the resistance reduction factor phi when computing the factored resistance phi Mn. So please watch lesson 7 for the procedure on how to compute phi. However, later on in this video, I briefly go over that process again. Now let's look at the case when the compression is extended into the web. In other words, A is larger than T. In order to find the bending resistance in this case, we divide the section into two parts as shown. So this is our section. Notice that the compression is now extended into the web. And we consider these to be made up of two components. We call the first component as F, and this one is made up of the overhanging parts of the flange, balanced by a small amount of steel, we call it ASF. Notice that the total width of the compression is BF minus BW over 2 plus BF minus BW over 2. So total is BF minus BW. The second case or situation is W, and in that case the overhanging parts are not there. The compression is only within the web, so it's practically a rectangular section. The remaining part of the steel is balancing with this compression area. So we have this case as W, the previous one as F. So please keep those in mind. With these two configurations, we find out the resistance provided by that F situation and with W situation, and we add the two, we get the total Mn. And don't forget that MNF can be found as ASF times Fy d minus T over 2, and the corresponding area of steel by equilibrium of tension and compression is 0.85 F prime sub C BF minus BWT divided by Fy. The good news is that these two values are independent of the total area of steel. So we see later on in design that they could be computed once and they always remain the same, no matter how we make a change to the steel configuration. Now, the MNW is the remaining area of steel times Fy times d minus A over 2. But then this A is different from the A we had in previous case. So we have to write the equilibrium for that situation W and find A. If we do that, we find out that the equation for A, although similar, is slightly different. First of all is ASW that is used in here. And secondly, you notice that is a BW that is used in the equation. And don't forget that ASW is AS minus ASF. Now finally, we need to find phi and multiply Mn by phi to have what we call the factored resistance. Now here let's have an overview of how to compute the resistance reduction factor phi. Knowing the dimension A, we need to compute the parameter x, which is the distance of the neutral axis from the extreme compression fiber. X is equal to A divided by a parameter beta 1. Beta 1 is 0.85 if prime sub c is less than or equal to 4000 psi, and it is equal to this equation when f prime sub c is larger than 4000 psi. However, the smallest possible beta 1 is 0.65. This equation simply implies that for every 1000 psi over 4000, we need to reduce the beta 1 by 0.05. However, in no case we can be below 0.65. That is the absolute minimum. Once we have x, then we compute the strain at the layer of steel, tension steel, which is closest to the tension face of the section. What do we mean by that? Well, this happens when you have several layers of tension steel in tension area. Epsilon T is a strain at the first layer when you count them from the bottom. The good news is that if you have all the steel in one layer, then D and DT are the same. Once you computed this strain, phi would be taken as 0.65 if this strain is smaller than 0.002. This is the smallest possible phi, and for this situation your section is not very economical, is not very optimum. However, if phi is equal to 0.9, then in that case your section is of course very optimum or very economical or very efficient, whichever way you want to call it. But that would be if this epsilon t is larger than 0.005. Actually, it should be larger or equal to. So this is the most efficient section. Now, what if my epsilon t is between the two? Then we use an interpolation using this equation. All right. Let's look at an example. We want to compute the factored bending stress phi Mn for the monolithic floor system shown in this figure. If prime sub c is taken as 3000 psi, Fy as 60,000 psi, and we are using 4 number 11 bars in 2 layers because we couldn't put them all in one layer. We could not put 4 bars in a width of 12 inches, so put them in 2 layers. Stirrups are number 3 bars. The clear span length for the beam is 20 feet. In other words, Ln, which is in the third direction, is equal to 20 feet. So it's that Ln is equal to 20 feet. The clear spacing between the beams is equal to 30 inches. The overall depth of the section is 18 inches. The slab thickness is equal to 3 inches. So with these dimensions, let's find out what is BF. After finding the BF, we need to determine whether the compression area is extended into the web or stays within the flange. So, if you recall, BF is a minimum of BW plus 16T, that gives us 60 inches, BW plus SW, that gives us 42 inches, BW plus ln over 4, that gives us 72 inches. Naturally, this is the value that we use for BF. Then we talk about the transitional AST. AST is 0.85 prime sub CBFT over Fy, and that is 5.35 square inches. Each number 11 has 1.56 square inches of area. Therefore, the total area that we are using is 6.24. As you compare it with this value, we realize that it's larger than that. What does it mean? That means the compression area is extended into the web. Therefore, we must compute two components that make up the total nominal strength Mn. First, let's find out what the effective depth d is. And because we have two layers, d and dt are different from each other. And considering the fact that each number 11 has 1.44 inches of diameter, we are using number 3 stirrups. We need to have at least 1 inch vertical clearance between the two layers, and then we have 1.5 inches of protection cover. Then we can compute D, and that would be equal to 14.19, which is measured, as you can see in this figure, to the center of the tension steel. D is a little bit larger because it is measured to the center of the first layer of steel from the bottom. That shows the difference between the two. All right, from this point on, let's compute the ASF first. Notice that I'm using pounds and inches throughout my calculations, and I come up with 3.83 square inches for ASF. And the corresponding resistance MNF is ASF Fy d minus t over 2. Again, using pounds and inches throughout the calculations, but then I divide the final result by 12,000, so I get the final answer in foot kips. That is MNF, 243 foot kips. The depth of the compression area can now be computed as follows. First, find out the difference between the two steels, the steel that is used, the ASF, and that gives me ASW, which is 2.41 square inches. Plug it in the equation for A, and now remember that in this case you use BW. And we get 4.73. And I plug it in the equation for M and W, and again converting everything into foot kips, we come up with 142.5 foot kips. All right, so the nominal resistance is sum of the two components, and that gives me 385.5 foot kips. The resistance reduction factor phi is now needed as a final step. Let's look at the strain at the layer 1 of tension steel. Now for that we use dt. And we also need x for that. So x is A divided by beta 1. 4.73 divided by 0.85, so it's 5.56. Put it in equation for epsilon t, we come up with 0.0053 inches per inch, which is slightly over 0.005. Therefore, our phi is equal to 0.9. Multiply that by Mn, we end up with the factored resistance for this section, which is 347 foot kips. Let's look at the procedure for design for reinforcement. In this situation, the applied factor bending moment Mu and the section dimensions are known. The unknown is the area of steel AS. The first step is to find out whether the depth of the compression area A is less than or greater than the slab thickness T. We can't use the previous procedure because we don't know the area of steel, and we need to find that transitional moment MNT as we discussed before. So we get 0.85 of prime sub CBFT times D minus T over 2 as transitional moment. Our required MN, if it is equal to mu divided by phi, if it is less than MNT, then A is smaller than T. And in that case, then the procedure is as follows. We compute the material ratio factor M, which is Fy divided by 0.85 prime sub C. Because we don't have the area of steel, we need to assume D as H minus 2.5 inches. And because the Mn is smaller than Mnt, remember that our section would be just like a rectangular section. So for that, we compute a factor called R, which is the required strength divided by Bf d squared. Now again, please note that here we use Bf. There will be another version of R appearing in this video, and for that one we have to use BW, so please pay attention to which B is used in the equation. And again, if you would like more information in design of rectangular sections, please watch lesson 7 of my video series. Now then plug those into equation for AS, and we get the area of steel that is needed is 1 over m, 1 minus the square root of 1 minus 2 mr over Fy, the quantity multiplied by Bf times D. Again, pay attention to Bf. And sometimes in my lecture videos, I call this portion of the equation as the steel ratio rho. So it's a steel ratio rho multiplied by the effective area. Make sure it is checked with the minimum amount of steel, which is larger of the two values, or if you want, use 4/3 of the required area of steel. Now this means that if area of steel that you computed here is smaller than the minimum, then rather than the minimum, you can use this 4/3 equation. After making sure the minimum required steel is met, select bars and compute the total area of bars you are using, and this would be new AS. Now why do we have to do it? Because the AS that you found from the equations cannot be exactly matched with the right number of bars, and you ended up with always AS that is a little bit larger, sometimes maybe even smaller than AS. So you need to make sure that at the end you have adequate strength to meet the requirements for design. So compute the AS based on the bars you selected. And by having the area of steel, now you can compute A, D, dt, phi, and Mn, which is equal to this equation. And then make sure that phi Mn is larger than Mu. Now, what if it is not? Then change the area of steel a little bit until this inequality is satisfied. Now, what if Mn, which is mu divided by phi, is larger than mnt? Well, we know in that case A is larger than T, and in this case the steel area is made of two parts, ASF and ASW, if you recall. So the procedure is as follows. First you assume D again as H minus 2.5. Compute ASF using this equation that I gave you before. Remember I said that this equation is independent of the total area of the steel, so always remains the same. And the corresponding resistance MNF now could be computed as well. Again, this remains constant, and assume phi is equal to 0.9, and let's determine what would be the MNW. MNW is mu divided by phi, which is the required strength, minus the MNF that you just computed. Now from this point on, compute ASW as you are designing a rectangular section, however using BW as the width. For that, compute the R factor. Here I'm going to call it RW, which is MNW and divided by BW, so please pay attention. And then plug it into equation for the area of steel. However, the area of steel is now called ASW, noting that it is multiplied by BW. Do not check this value with the minimum yet. First, you need to add it to the area of steel you computed before to get the total area of steel, and now compare it with the minimum. Again, the minimum is the same. The equation is the same. It's larger than this value and this value. with BW used in both equations, or 4/3 of the required area of steel that you computed. So you now select bars, and by selecting bars, you have the entire section known. So you can compute d, dt, and phi. Go over the exercise as we said before, and compute the MNF and MNW. NMF doesn't change, it's MNW that change. And get the total resistance with the correct phi computed. Find out that the phi MN is larger than MU. What if it is not? The best solution is to increase the area of steel a little bit, change the configuration, noting that ASF doesn't change. That change would affect ASW, and that would increase MNW and will fix this problem. Let's look at an example. In this example, we wish to design reinforcement for a beam with a cross-section shown. Let's examine this cross-section. The width is 16 inches, thickness of the slab 3.5 inches, BF is 38 inches, and the overall depth of the beam is 20. See, the only thing we don't know is the area of steel. The material selected, F prime sub C is 3000 psi, Fy is 60,000 psi. Mu is given to us at 441 foot kips, which is obtained based on some type of structural analysis, with number 3 stirrups to be used. And don't forget that Mu includes all the pertinent load factors. So our resistance ratio, capacity of this steel to that of concrete, is 60,000 divided by 0.85 times F prime sub C is 23.53. So what's the first step? We want to determine whether the compression area is extended into the web or not. For that, we need to compute the transitional resistance MNT. And I gave you the equation before. So for that, please find D first, estimate as D H minus 2.5. Plug it in the equation for MNT. Using inch and pounds in the equation, at the end we divide it by 12,000, so we get foot kips. All right? And the required resistance is Mu, which was given by the problem, and divided by 5, which is now assumed. We're going to check it later. And notice that this is larger. That means A is larger than T. And the compression area has therefore extended into the web. So find the ASF and MNF. Remember that these things won't change. ASF, plugging the numbers here, ends up with as 3.27. Put that in the equation for MNF using pounds and inches, and at the end divided by 12,000, we get this much, 257.5 foot kips strength provided by that F component or F situation. Now, these values will not change, as I said. We don't have to modify them. The only modification would happen on ASW, as I said. But what is ASW? First, let's compute MNW, which is the required strength minus MNF we just computed. That's 232.5 foot kips. We find out the area of the steel ASW. For that, don't forget the BW is used. So let's find out RW. Make sure that you're using inch and pounds so that you get 569.4 psi. Again, this has nothing to do with stress. It's just the unit for that is psi. So I plug that into equation, knowing that BW is used in the equation. I end up with 3.05 square inches of steel area. I don't compare it with minimum yet. I add it to ASF and I get a total area that is needed at 6.32. Now I compare it with the minimum. The minimum is larger of these two values, and it's going to be very small anyway, 0.94, and that one is certainly not larger than that, so the value we're going to use would be this one. So what do we use in terms of the bars? I am suggesting 5 number 10. The width is 16 inches. So is this spacing okay? Yes. What you need to do is that, considering the fact that each number 10 has a diameter of 1.27. Number 10 is a very peculiar bar. It has an area, cross-sectional area is 1.27. Numerically, its diameter is also 1.27. So you get 5 bars, 5 multiplied by 1.27, plus you get 2 stirrups, so 2 times 3/8 inch, plus you get 1.5 inches of protection cover from each side. So that is the space occupied by the bars, the stirrup, the protection cover, deducted from the total of 16, and then divided by the number of spacing, which is 4. The result should be larger than 1 inch and larger than the diameter of the bar, which would be in this case. So we can pretty much fit 5 number 10 within that 16 inches of the width. But you notice that now we are using 6.35 square inches versus 6.32. So it's slightly larger. I mean, we can just say this problem is done. But I just want to show you that a lot of times this difference is a little bit larger than just a 0.03 that is in this case. So what you do, you find out the new ASW, which is the difference. Remember, this doesn't change. This is ASF that doesn't change. So our new ASW is this much. Then this one in the equation. And before that, let's figure out what is the exact value for D. And D and DT are the same, so we don't have to compute two different values. And compute A, which is using BW. So that's 4.53 inches. The location of neutral axis is A divided by beta 1, which is 5.33. And as I said, D and DT are the same. So find the epsilon T. We showed the exercise before. In this case, it's a 0.0068, which is larger than 0.005. Therefore, our phi is equal to 0.9 as we assume. Find the new M and W by plugging the correct ASW in the equation. Again, inch pounds divided by 12,000. So you get 234.5 foot kips. Add it to M and F, multiply by phi. You come up with the available factored resistance as 442.8, which certainly is larger than the applied moment. Our design is therefore okay. Let's look at another example. In this one, the configuration is given. BF is 60. Thickness of the slab 4.25. H 24. BW 18. So what are we looking for? We want to design steel. What are the material properties? 4,000 psi concrete, 60,000 psi steel, MU by calculation is 650 foot kips, and we have number 3 stirrups again. So our M factor, which is a ratio of the strength of the steel to that of concrete, is in this case 17.65. So why it is smaller than before? Because we are using a better quality concrete. So our first step again is to determine whether the compression area is extended into the web or not, and for that we need that transitional bending moment. Let's assume again D as H minus 2.5, and the transitional moment is the equation I gave you before, making sure units are working out, and we are talking about 1,399.8 foot kips. So how much strength do we need? 650 divided by 0.9, 722.2, smaller than the M and T, so A for sure is smaller than T. And as such, the beam will be simply designed like a rectangular section, with the width B equal to BF. So please watch lesson 7 of my series on structural engineering made simple that talks about design of rectangular sections. So find the R factor, and don't forget that this uses BF in the equation. R is equal to 312.5 psi, and plug it in the equation for AS and multiply by BF and D. The answer is 7.06 square inches. So now let's check it against the minimum. And don't forget that in this case, the minimum always uses BW. So this is one of those confusing parts because the area of a seal uses BF. But when it comes to equation for minimum, we use BW. So certainly we are larger than the minimum. We don't have to do anything else except that we select bars. So I suggest 3 number 11 plus 2 number 10. You might have a question, why you are mixing bars? Why are you using the same size bars? We are allowed to mix bars to get as close as possible to the area of steel that we need. When you are mixing bars, make sure that the difference in the grade is not more than 2. This is like a number 11. This is number 10. So the difference in the grade or the size, whichever you want to call it, is just 1 difference. So you can use it. I could have used number 11 and mixed with number 9. But I could not combine, let's say, number 11 and number 8 or number 7 because the difference in the grade, or you may want to say size, is really more than 2. So in this case, knowing that number 11 has an area equal to 1.56, number 10 has 1.27, I get 7.22 square inches. The question is, can I put them in one layer? Yes, you could. Again, check the spacing. For that, you can use the diameters of the bars. You already know what they are. And the protection cover, use it as 1.5 on each side. And usually for computing D, when we have mixed bars, conservatively, we can use a larger size bar. So in this case, get 21.41. I plug it in the equation for A, and remember that in this case, BF is used. So I get 2.12 inches. And the corresponding location of neutral axis is 2.49. Because D and DT are the same, I can find the epsilon t very easily, and it's 0.023, which is much larger than the threshold value of 0.005. So our phi is equal to 0.9. Now let's compute the capacity, Mn, or resistance as sometimes we call it, 7.22. That's the area of the seal we are using. With all the numbers that we computed, making sure units are okay, we get 734.6. Reduce the resistance, or what we call factor resistance, when you multiply that 0.9 is 661.2. Certainly that's larger than 650, so our design is okay. The procedure for reinforcement design of a T-section explained in this video is applicable for most general cases. Please make sure to go through the ACI for a complete review of all requirements for special cases of isolated and also pre-stressed T-beams. Design for shear reinforcement is similar to that in a rectangular section. It is the same for all flange section, that is the shear design, regardless of whether the compression area is extended into the web or not. This is because the concrete shear resistance area is always BW times D. In other words, it is independent of the flange width. Please watch lesson 8 of my YouTube series on structural engineering made simple for review of shear design. Thank you for watching this video.